emerging pollutants is used to define any synthetic or natural occurring chemical or microorganism that is not commonly monitored or regulated in environmental compartments, meaning groundwater, surface water, drinking water, wastewater, soil, and food. Some of these chemicals display known adverse ecological or human health effects, such as pesticides or hormones. Others are suspected to display adverse effects, but thorough toxicological studies are lacking, as in the case of nanomaterials, whose safety evaluation is an active research area that requires also the development of new methods to address their special properties. These contaminants include compounds of different origins and nature that, thanks to continuous improvements in analytical techniques, can be and are being consistently detected even in low or very low concentration in different environmental compartments. They raise special concern because their presence in the environment or the consequences of their presence have gone largely unnoticed, as their long-term adverse effects. Accordingly, these contaminants are collectively defined as emerging or of emerging concern, with the term emerging which applies to both the contaminant and the resin issues. In fact, these contaminants comprise not only new or recently introduced chemical, but also well-established chemical used in large quantities in everyday products that may have been long present in the environment but only recently detected. This is the case, for example, of perfluorinated compounds, usually abbreviated in PFAS, and bisphenol A, belonging to the chemical family of alkyl phenols. Emerging contaminants can be classified in several ways based on their origin, use, potential effects, or environmental fate, but unfortunately these categories can overlap, leading to some confusions. The major groups include pharmaceuticals and veterinary products and their metabolites, biocides and their byproducts, illicit drugs, personal care products and other lifestyle products and their metabolites, industrial chemicals such as surfactants and flame retardants, pesticides, food additives, water disinfection byproducts, nanomaterials, waterborne pathogens, and biological toxins. Some of them are known, probable, or suspected carcinogen, display endocrine disrupting effects, or negatively interfere with normal hormonal activity. All these chemicals may enter the environment in multiple ways, depending on their pattern of use, production, usage, and disposal. Generally, wastewater discharge is the most important source of emerging contaminants spread at the global scale. Releasing during production processes or incorrect waste disposal are less important at a global scale, even if they are responsible for relevant local impacts next to industrial plants or illegal landfills. Such a wide number of molecules correspond to quite different chemical physical properties and behavior, which differently affect their fate and transport in the environment. Properties influencing environmental mobility affect also the possibility for these compounds to enter the food chain through contaminant uptake by crops from soil and irrigation water. Anyway, the transfer and bioaccumulation of many emerging contaminants in the food chain remain relatively unresolved. As a matter of fact, many of these compounds can be considered ubiquitous, and mitigation action are required to reduce their concentration at acceptable level in drinking water, while no specific controls are performed on bottled water or food, which represents other exposure routes for humans. Similarly, an understanding on the long-term effects on ecosystem and human health is still lacking in many cases. Human health-based reference values or environmental standards are still unavailable or only provisional and are continuously updated due to new findings and improved knowledge. Most of these compounds are not included in actual regulation and are not submitted to routine monitoring and/or emission control regime. Moreover, to even complicate the framework, both environmental processes and removal processes within treatment plants may transform emerging contaminants, generating several metabolites and byproducts whose properties are as yet undetermined as well. Manuela, tell us about two significant examples.
The first one is related to PFAS. PFAS comprise per- and polyfluoroalkyl substances, a class of thousands of synthetic molecules used since the 1940s in a staggering array of consumer and industrial products, such as food packaging, water and oil-repellent clothes, paper protection, and firefighting foam. PFAS are often referred to as forever chemicals due to their incredible persistence in the environment and organism. For instance, a recent study by the US Center for Disease Control and Prevention estimated about 95% of Americans have detectable PFAS in their bodies. PFAS have been identified as toxic for the reproductive and immune systems and probable carcinogens. Due to their unique chemical features, PFAS are widely applied in the industry as surfactants, and we often encounter PFAS in our everyday life, such as in apparel and shoes, in pots and other cooking utensils, in food papers, and so on. As PFAS usage is continuously increasing and due to their bioaccumulative and persistent properties, they can now be detected in drinking waters all over the world. PFAS can be removed in drinking water treatment plants only if appropriate treatments are present, and the most relevant one is adsorption on activated carbon. Anyway, treatment costs can increase also relevantly, since the activated carbon lifetime with respect to PFAS is shorter than the one for other contaminants, causing a more frequent replacement of the material. Besides, recent studies have raised doubts about the possibility to reuse activated carbon used for PFAS removal, determining a higher environmental impact and reducing treatment sustainability. In addition, since PFAS have common exposure routes, they affect the same endpoints, but with differences in toxicity levels. Then, mixture risk assessment should be applied to fix appropriate reference levels and to manage treatment processes for minimizing the risk. Another relevant example is related to bisphenol A, a plasticizer used in food and water contact materials. Therefore, humans ingest BPA from potentially contaminated drinking water in the case pipes have released this compound, bottled water due to the release from a plastic bottle, food that has been packed in plastic films or plastic boxes. The knowledge about BPA effects has been recently updated both in terms of critical endpoint and concentration level. In 2015, the critical endpoint was identified in the decreased kidney weight, while in 2021 it was changed in the immune system, fixing a reference dose of 0.04 nanogram per kilogram of body weight per day. When multiple exposure ways are possible, as in case of BPA, it's fundamental to consider all the exposure routes to evaluate the risk for human health, in order to identify the most critical one, where efforts for concentration reduction should be applied. In conclusion, we and our planet need responsibility in the use of chemicals at all levels. Not only chemical industries, but also user industries, treatment plant managers, and last but not least, consumers who can push towards a more sustainable lifestyle.